record. So, oh, I need to share too, don't I? Share like this. And you need to see that one. So, bio means life, and geo means rock. So, let us look at what we're going to be doing today. We're going to be talking about the biogeochemical cycles, right? And then we're gonna go over the module for mastery kind of close to the end, and we're gonna talk about atoms and compounds and the formation of minerals. So it's gonna be fun. But go ahead and answer in the Pear Deck. What do the carbon, oxygen, nitrogen, and phosphorus cycles all have in common? Er, what about your dad?
I learned about this last year, and I still can't remember.
I've learned something like this last year as well. I've learned some of the things we learned from last year.
Yeah. Well, a lot of
And
things
honest,
take repetition for us to remember, and that's okay.
even though I've been in school for a while, I still hardly can remember anything.
I can relate.
So, we've got one person saying they're all open systems. They all bring organisms nutrients so they can survive. They happen on Earth. Um,
I believe the same reason. Sometimes I do think it's a close too.
so these are all part of the Earth systems, right, that we talked about last time. And so it's as a whole system, the Earth is fairly closed, right? It doesn't exchange matter really with the outside with the universe, for the most part. They are all cycles. They're all part of Earth's atmosphere. Ooh, that's interesting. They allow nutrients for the Earth. Okay. Okay, they recycle the nutrients. Yes. Okay, so let's look at them in a little bit more detail. Oh, you got to be kidding me. That's weird. Okay. So, biogeochemical cycles are cycles of matter, right, that happen between life and the earth and various chemicals. Okay. Um, to, and it's a cycle of various nutrients through the system of Earth. Okay. There's the hydrologic cycle. So let's start with that one. That would be the hydro cycle, the hydrologic cycle. That's fine, Emily. Thank you for letting me know. And that would be water, right? Hydro means water. Okay. So the hydrologic cycle is water, the water cycle. Okay. Water evaporates from the ground, it condenses into clouds. The clouds precipitate various forms of water back to the earth, and then it runs off to various places, right? So it cycles between locations, it cycles between states of matter, right? Solid, liquid, gas. Um, and water is super important for pretty much everything here on Earth, okay, but especially for life. Other cycles, we've got the carbon cycle, right? Carbon is an element that is necessary for life, right? Um, So carbon is a really, really special atom that can do things that not a lot of atoms can do. And because of that, it is the basic building block for life. It's really, really cool. But carbon cycles through the atmosphere, through the ground, through living organisms, right? It changes form. It bonds to other elements to form various molecules and compounds that are necessary, like carbon dioxide, right? We breathe carbon dioxide out. Trees and other plants breathe carbon dioxide in. Okay. They turn the carbon dioxide into parts of themselves, like their leaves and their branches. And then those get eaten by animals, like insects, which get eaten by bigger animals, like frogs, which get eaten by bigger animals, like foxes. And then we eat those, right? So, and then eventually things die, organisms die, right? And their carbon gets released as methane or carbon dioxide or leaches back into the soil, okay, during the decay process, kind of depending on what's going on. So, uh, we've learned how with our technology to how to mark a carbon atom and track it through the entire cycle. It's really cool. We can watch it happen in real time. Um, okay. Oh, forgot some pictures here. Okay. So you can see some more pictures here of the carbon cycle. Um, it's pretty cool. Next, we have the oxygen cycle. Okay, which we don't always separate this one out, but same sort of thing, right? It's a byproduct from plants. It's something we need to do metabolism, right, in order to get energy for our cells. There's the nitrogen cycle. Nitrogen is 78% of the air, guys. Nitrogen is the key element in amino acids, which make up proteins, and proteins do everything in your body. And nitrogen is the key element in DNA and RNA, deoxyribonucleic acid. Okay. And nucleic acids have nitrogenous bases. Okay. So you have to have nitrogen. You can't live without it. But the nitrogen we breathe in, we can't use. We can't use it like that. And so it goes through these cycles. And in that process, there's bacteria in the soil that take the nitrogen from the air and break it down and change its form into ways that we can use it, right? And then that gets into the plants, and then the plants get eaten, and so on, right? Okay, so these cycles, every part of these cycles happening correctly is super important for life. Yes, Adeline.
So this reminded me of something.
Hmm.
When you're doing or when you're setting up an aquarium, like especially a larger one, you need to use the nitrogen cycle to get healthy bacterias into a tank. It's called a cycle. And so you kind of need to understand the cycle really well so you can um like get that healthy bacteria into a tank that will keep your fish alive for longer.
Yes. Yes, exactly. That is a perfect example of how we use this stuff in everyday life. Anybody who's interested in fish and having aquariums needs to know that. Like you said, that's thank you. Thank you. Um, and if you guys have ever set up a saltwater tank, they're even more important. Okay. So we also have the phosphorus cycle. Hold on. I got to answer something here in chat. It's not going to let me do that, is it? Okay. So there's the phosphorus cycle, which again is really, really important. And we might not necessarily think about that, about phosphorus as a really important element, but the molecule that we use for energy in our body is called ATP, okay? Adenosine triphosphate. So you need phosphate in order to cycle the energy molecules in your body so that your body actually will do things. So your proteins do things, and the energy your proteins use to do things is phosphate, is ATP. Okay, so if you don't have enough phosphorus, your body can't make ATP, which means none of your proteins, including your muscles, like your heart, are going to work, and then you die. Okay, so having these cycles working properly is really, really, really critical for life. Okay. And every part of these cycles affects the other cycles, right? And like the precipitation from the water cycle helps to wash elements like phosphorus and nitrogen and carbon down from the mountains, right, into the water down that the animals drink and that the plants use in themselves, right? And so uh, again, they all influence each other. Okay, they're not independent of each other. That is okay, Victoria. So let's talk a little bit more about these specific parts, these atoms and these compounds. We need to know what the difference is. We need to know how we organize them and things. Okay, so we've got a few key vocabulary terms here. We've got an atom, we've got a molecule, we've got an element, and we've got a compound. Okay, an atom is the smallest part um, of an element that exists and has all the properties of that element. Okay. So anything smaller than an atom, any subatomic, right under an atom, so any subatomic particles don't have the properties of the element. They have to be together in an atom. Okay, so you've got atoms. When you get multiple atoms together and bonded to each other, you get a molecule. Okay, so a molecule is two or more atoms together. A compound is two or more elements. Okay, so I can have a molecule that isn't a compound. Okay, but every compound um, has molecules in it. Okay, or atoms in it, even. What's interesting about a compound is that it can be all one element, or it can be um, multiple elements, but it's all one single, what's the word? Thing, all one single thing. So let me give you an example. Okay. So a molecule is going to be the smallest unit of a compound. Okay. Sodium chloride is also known as table salt. Okay. There are two atoms in sodium chloride. Okay. And the compound is known as sodium chloride or table salt. Okay. So, but I could have, a cup of table salt and that would all just be considered a compound. Right? It's all the same stuff. It's all table salt. Okay. It's hard to see here on the screen, but we have things called diatomic molecules. Diatomic molecules are special. They're very special. There's only a few of them out there. Um, remember, di means two, right? Di mean it's a prefix for two. So diatomic molecules are molecules with two atoms of the same kind. We see, and that's how they occur in nature. So we're going to look at a few of these atoms, molecules, elements, compounds. Look at them. Okay. So I want you to tell me in the pair deck, what do you notice about these two types of bonds? All right, we got two situations going on here. What's different about these? Okay. Squares and dots, yeah. Um, a dot. Okay. So those dots represent things. These are symbols, right, that represent specific thing. Ah, yes, Trinell. Yes, you've got it. Um, One is what we would call an electron transfer, and the other is sharing of electrons. Okay. So the letters here represent specific elements, okay, specific atoms in these cases, and the dots represent the electrons around those atoms. Okay. Kat said the sodium atom, Na, is not a part of the chlorine atom, unlike the HOH are connected. Yes, that's great. Okay, so let's talk about this. What does this mean? Okay, well, we've got well, we don't go over the third one here, but we've got three different kinds of chemical bonds. We have an ionic bond, a covalent bond, and a metallic bond. Okay, an ionic bond is where you have two ions. An ion is a charged atom, an atom with an electrical charge, which means it has too many or too few electrons based on what it should have. Okay. It should have the same number of electrons as it has protons. Okay. That way it's balanced. But things change very quickly in nature. So a lot of atoms will form ions. They'll drop electrons or they'll grab extra electrons. And things like to be neutral. They like to be balanced. So you'll get these ions, one that's positively charged and one that's negatively charged, hanging out together. That's how we get table salt. Sodium is positively charged, which means it dropped an electron. Okay. It's missing an electron. Chlorine is negatively charged, which means it has an extra electron. And because they both have a, a one charge, right? One has a plus one charge, the other has a negative one charge. Okay. Um, they hang out together and they don't really share their electrons, but they stay near each other so that they feel balanced, you know? Um, so Riley, I am not sure what you are asking there.
So basically, what I mean by that is like, you know how like some water is like really dirty?
Uh-huh.
So like all you really have to do is just like take like a coffee filter, put it like in a cup, right? And put like rocks and dirt in
Hmm.
it and like it goes, hold on.
And you run it through it and it comes out clean. Yeah. So that is what we would call a physical filter. Okay. And what that does is it just blocks the bigger chunks from flowing down. Um, just like anything, like just like a wall blocks light. Okay. Um, there are physical filters that just block the bigger chunks of stuff. Now, these chunks are still small when we look at them, like to our eye, but if we were to zoom in with a microscope, they would look really, really big. Okay. And the holes in the coffee filter are really, 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 really tiny. So it's enough for molecules of water to get through, but not enough for big chunks of dirt to get through. And again, when I say big, I mean big comparatively speaking. A chunk of dirt, a couple hundred, couple thousand atoms maybe. A chunk of water, well, water can be separated into a single molecule, which is maximum three atoms, right? So three atoms compared to a couple hundred, it's easy to see how one could get through a space while another couldn't. Okay. Yes, Adeline.
Would a couple hundred atoms still be microscopic though?
Oh, yeah. Yeah, absolutely. Atoms are super tiny, super tiny. We're talking like a trillion times smaller than you can see with a microscope. Rightly.
So I was about to talk about it, but my sibling knocked on my door. But
Yeah.
sorry.
Did you hear the answer at all?
What?
Did you hear my answer to it?
Um, Basically, like big chunks of dirt can't really pass through.
Yeah.
So it's like the Earth's natural way of filtering water,
Yes.
right?
Yeah, that's that it does happen naturally a little bit. Coffee filters obviously aren't natural, but there are,
Yeah.
you know, other things that do that naturally. Okay,
Yeah,
so we've
because we learned it. We kind of learned it last year, but we didn't learn why.
yeah. Yeah, that's just a physical filter. There are other types of filters that we're not going to talk about right now. But okay, so we've got ionic bonds, right? We got a positive and a negative charge hanging out together, making each other feel neutral and safe. Okay. We also have covalent bonds. This is a sharing of electrons. Okay. Neither of these elements wants to fully give up their electron. Um, and neither of them is really strong enough to take the electron from the other one. So they just kind of share it. And that electron kind of hovers between them. Okay. There are two types of covalent bonds, polar and nonpolar. And when you think about polar, right, you think about the poles of the Earth, right, or the poles of a magnet. There's ends, right? So with a polar covalent bond, they're not sharing it equally, right? One of them's a little stronger than the other. That electron is hanging out closer to one of those elements than the other. Um, Non-polar, they're sharing it equally. There's no sides. Okay. Water is special because it has an extremely polar covalent bond between the hydrogen atoms and the oxygen atom. Okay. And that creates a lot of special scenarios that have led to life. Okay. There's a lot of special things that water will do because of that polar covalent bond that a lot of other things just can't. Okay. It's one of the reasons we look for water when we're trying to determine if there might be life out there. Okay. Now, a chemical reaction happens between elements or compounds, and what happens is electrons get moved around and you get something new. Okay. So if I take pure sodium, it's a hard metal. Okay. Well, kind of. It's a soft metal. It's a silvery metal, solid. And I take chlorine, pure chlorine, which is a gas, and I throw them into the same container, shake it up. They're going to mix together, and I'll probably get salt out of it. Okay, something completely different, all because those electrons moved around. Okay, so that's a chemical reaction is just the movement of electrons between atoms or compounds, causing things to change. So, another chemical reaction you could have here is between magnesium and oxygen. You take magnesium, solid metal, mix it with oxygen, a gas, throw them together, add in a little bit of energy, and the electrons will move around, and you'll get magnesium oxide. Okay. What do you guys notice about the magnesium before and after?
It's like combined.
Yeah, we've changed how we spell it, right? We've changed how we write those symbols, okay? Anything else?
They're not exactly the same, even though you think it would be, but it's not.
What do you mean by that, Riley?
Like, since like you added a new thing to it, it makes like a whole new like
Yeah. Yeah, it makes a
thing.
brand new compound, okay?
Yeah.
Um
And you can notice that the two's not there anymore.
the two on the oxygen?
Yeah.
Yeah, that two on the oxygen isn't there. So before the chemical reaction, that there were two oxygen molecules bonded together. Afterwards, the oxygen is bonded to the magnesium now. Okay. Okay. What about this? We've got a couple of vocabulary terms, a couple more vocabulary terms. We've got reactants and products. Which side is the reactant side? Is it A or B? Go ahead and tell us in Pear Deck. Riley, you have a question?
Oh, no, I was gonna answer it, but
Oh, okay.
I already
I'm going to let
answered
a
it
couple
in
more
Pear
people
Deck.
answer on the Pear Deck first. This one's a little tricky. So it turns out the reactant side is always written on the left. Always. Okay. The product side is always written on the right. And those arrows in between tell us. Okay. The arrows tell us the direction that that reaction is happening in. Now, I'll be honest. This isn't the direction this reaction usually happens in. It usually happens the opposite way. But it's not this time. It's going from water to hydrogen and oxygen, which that can happen. There are scenarios where that happens, okay? But the reactant side is always, always, always on the left. Something else we need to know is something called balancing equations or balancing reactions. We call these things chemical equations, okay? And they're equations because the left and the right are equal. So what's equal are the number of each atom that we have on both sides. Okay. To do that, you have to balance the equation. You have to change those numbers in front of the elements, in front of the compound names, so that you have a balanced chemical reaction. Okay. So if we count these up, okay, we look on the left here. Make sure I've got a good color here. Sure. Because white I can't see. Let's make it green, guys. So right here we have two hydrogen atoms, right, for every single water molecule. Okay. And we have two water molecules. So two times two is four. That means we have four hydrogen atoms on the left. Okay. We also have one oxygen atom or per every water molecule, and we've got two water molecules. So we have two oxygens on the left. Now, if we look on the right, we've got our two oxygen atoms right here. Okay, that's good. We've got two on the left, two on the right, and we have two hydrogen diatomic hydrogen molecules, and each of those has two hydrogen atoms. So that's four hydrogen atoms total. Okay. Cool. So we are balanced here. But what happens? Like, let's see if we can determine if another one is balanced. Okay. So coefficients, right, that number in front, are used to help us balance. Is this equation balanced? Do I have the same number of each atom on both sides?
Did you say number or letter?
Number, the same number of each atom. So you'll always have the same atoms on both sides, but you need to have the right amounts too.
It's a little different
Okay, tell us what's
because,
different about it.
well, the on the CL there's the two, but if you look over, there's no two on that, and the two's in the front.
Oh, so that two, that's a very, very good observation. That two on the bottom right, that's a subscript. Okay. That tells us how many of those elements are bonded together, how many of those atoms are bonded together in that element. So on the left, we have chlorine with a subscript two in the bottom right. That tells us every chlorine molecule has two chlorine atoms bonded together. Okay. Now, the number in front, the coefficient, like we see on the right, in front of the compound, okay, so the chemical compound would be NaCl or sodium chloride. Okay, that two in the front, that coefficient, is telling us that we have two of this molecule. Okay. So if we count these up, let's do that. Okay, I've got one sodium on the left. I've got two sodiums on the right. I have two chlorine on the left, and I have two chlorine on the right. Okay. That's not balanced, right? So the way to fix this is I am going to put a 2 in front of this sodium, okay? And now it's balanced, right? Now I have two sodium atoms on the left, two on the right, two chlorine atoms on the left, two chlorine atoms on the right. Okay. So that balanced chemical equation should look like this. Okay. Um, you're not going to have to balance them at this point, but you need to know that they have to be balanced when we're doing the math and writing this stuff out. It's because of the conservation of matter, the law of conservation of matter. It means that atoms don't just disappear. Matter doesn't just come out of nowhere and doesn't go to nowhere. It's all the same. Okay. Now we have two more vocabulary terms, right? Um, we've got heterogeneous and homogeneous.
Hey,
Okay.
can I say something?
Yes, Damien, what's up?
Two things. Somebody had a question, and two, anyone who's an Uno fan say what?
I don't think anybody's going to fall for that, dude. Sorry. There was a question, and it was back here. We haven't quite gotten to the answer yet. Evie, do you have, you got your hand up though?
I was gonna say, I'm very familiar with these two. They're basically like, so hetero is basically the different mixtures, and homo is like these same mixtures.
Yeah, so hetero means different, right? Homo means same. Okay. So heterogeneous means that that there are different things mixed together, but they're not mixed together evenly. I could take a scoop out of one side of it and a scoop out of the other side, and they're not going to be the same amounts of stuff. A homogeneous mixture, it's all mixed evenly. Okay. So in a homogeneous mixture, everything's mixed evenly. No matter where I take a scoop or a sample out, they're all going to be the same. Heterogeneous, I could take samples from different spots and they'll be different because it's not mixed evenly. Okay. Now let's answer that question. Adeline asked a really, really important question. Probably, I don't know, a while ago. And she said, why are some solids really, really hard and some are soft and malleable and movable? Well, it all comes down to the characteristics, to how these minerals and these solids form, how the atoms share electrons and interact with each other. Okay. So a mineral is a very specific type of solid. It's naturally occurring, so you'll find it in nature, and it's inorganic, which means there's no carbon. Okay. It also has a definite crystalline structure. Okay, that means that I can zoom in and those atoms are going to be in very specific locations related to each other every time. Okay, it's going to form very specific shapes inside there. Okay, but we see, like on an atomic level, we see lots and lots and lots and lots of minerals out there in nature. Okay, so let's see if we can identify some minerals. Okay. Remember, there's 5 characteristics that have to be true. It has to have a definite chemical composition. Okay, so specific atoms bonded together in specific ways. It has to be a solid, so it can't be a liquid or a gas. It has to be inorganic, no carbon. It has to have a crystalline structure, which means those atoms are rigid in specific shapes when I get to the atomic level. And it has to occur naturally. So let's look at some. Quartz has a definite chemical composition. It's silicon dioxide. There's one silicon atom for every 2 oxygen atoms, and they're bonded together. There's pyrite, which is iron silicide. Okay. There's one iron atom for every two. Oh, so sorry, that's iron sulfide. One iron atom for every 2 sulfur atoms, and they are bonded together. Minerals are always a solid. That's a good joke. Oh man. They're always inorganic. They are not connected to life. Okay. And when I say connected to life, I mean they are not they're not usable. Well, so they are usable. It means there's no carbon theoretically. Okay. But there is actually one mineral that is carboniferous. Um, okay. So we'll talk about that in a little bit. It has a crystalline structure. Okay. So those atoms are in rigid, fixed positions. You can see some examples of that here on the right. Okay. And those atoms are not moving around relative to each other. Okay. You could have a chunk of the crystal move around, right? Or not. Okay. And again, it happens naturally. Okay. So here's a question. We got liquid mercury. Is that a mineral? Does it fit all 5 of those?
Can I say something?
Say again, Orion.
Can I say something about this?
Yeah, what's up?
So we're talking about, wait, mercury, right?
Yes.
Well, we do know that it is a chemical compound, but mercury itself is solid, but it's liquid, so it's not. So it does not meet the requirement.
You're right. So mercury does not meet the requirements for a mineral. It's not a solid. It is a liquid at room temperature. Okay. In nature, we find mercury as a liquid. Okay.
Someone has a question
Say again?
in the chat. Someone
Yeah,
has a
no,
question
I
in the
see it.
chat.
So when we're looking at the names of compounds, okay, let's go back here. So right here. Okay. These numbers tell us different things. Okay. When it's on the right and down at the bottom, it's a subscript that tells us that there are two of those elements bonded together. Okay. When it's on the left, it just tells us there are two of that compound. Okay. So on the left side of this equation, we have two sodium atoms and two chlorine atoms, but the chlorine atoms are bonded together. The sodium atoms are not. They're just hanging out. On the right, we have two sodium chloride compounds. Okay. Okay. So what about this? Is this chunk of coal, is that a mineral? Yes, Adeline. What's up?
I just wanted to ask, can you freeze mercury if it's liquid at room temperature?
Absolutely. So freezing is technically just
Hold
like
on, hold on.
scientifically speaking, freezing is the process of changing something from a liquid
I got a
solid.
question.
Hold on, Damien. Hold on. So freezing is the process of changing something from a liquid to a solid, and you can freeze pretty much anything if you have the right conditions. Um, Mercury is not difficult to freeze. It turns into a solid before you hit 32 degrees Fahrenheit. So,
Can you
okay,
melt
Damien,
coal?
what what was that?
Can you melt coal?
Not at atmospheric pressure, no. Damien, what's your question?
So, if I'm correct, you can tell me if I'm correct or not. If you compact obsidian, wouldn't that wouldn't that make the obsidian harder than it is?
That's a good question. No, you can't compact obsidian. Not possible. Um, and it has to do with its crystalline structure. Uh, If you squeeze obsidian, it will shatter into smaller pieces. Okay. So the answer for this one is coal a mineral? No, it's not inorganic. And coal doesn't have a definite crystalline structure. Okay. Good job, Trina. Ice, is that a mineral? Ooh, this one's tricky. You could answer yes or no. It is inorganic. It does have a definite crystalline structure. It is naturally occurring. It is a solid. It does have a definite chemical composition. But it's really, really hard to find pure water out in nature. Really, really hard. Usually you have other things mixed in with the water. So if the ice is pure water, if there's nothing else mixed in, yes, it would count as a mineral. If it's if it doesn't, or if it's not pure, if there's other stuff in the water, it would not count as a mineral. So, okay, sulfur, that is a mineral. Okay, so minerals generally, a lot of them form from cooling magma, okay, or cooling lava. Remember, lava is when it's on the surface, magma is when it's below the surface, okay? And the rate at which it cools, so how fast it cools, determines what that mineral will be. It will, because it determines that crystalline structure. The more time that those atoms have to shift and move before it becomes a solid determines how they're going to end up in relation to each other. So, what about these guys here? Which of these rocks contain minerals that took the longest to cool? Yes, that is obsidian on the right. It's granite on the left and a different type of granite in the middle. Yeah. Yeah. The answer here is A. A took the longest to cool. You got the largest individual crystals inside that. Okay. C cooled the fastest. C actually cooled the fastest. You can't see any of those chunks of crystals in there. Okay. We do not have time to do the book it today, but this is linked in the
Can we
on the
do
class
it
page.
next week?
So, well, next week that assignment will be passed, so we'll probably run out of time. We've run out of time, unfortunately. Sorry, but you guys can do the book it. Okay. So here is our exit ticket. You'll see it linked there. I'm going to paste it into chat. And our password for the exit ticket today is molecules. Go ahead and stick around if you have questions. If not, thank you for being here. Thank you for asking questions. Thank you for participating. Adeline, did you feel like I did you hear that answer to your question there about why some solids are hard and some are not?
Yes.
Okay. So yeah, it all has to do with that crystalline structure and the elements that are involved. So,
Bye. Thank you.
yep. Bye guys.
Bye. Have a blessed day.
Bye.
Bye. It's
Bye.
Favorite class of
molecules.
the week.
Bye.
See you
Bye.
guys. Thanks.
Bye.
See you guys.
Bye.
Yes, Valentine.
What's the word for the exit ticket?
Molecules.
Goodbye.
Sorry.
Bye guys. See you, D'Angelo. Bye, Haley. Bye, Victoria. Bye, Joseph. Have a great day.